Welcome. I'm Peter Marbach from the University of Toronto, and I'm presenting our paper, Optimal Bidding Strategies for Online Ad Auctions with Overlapping Targeting Criteria. This is joint work with my former student, Eric Tilburg, and with Ravi Masumdar from the University of Waterloo. The research has been supported by Pelmorex Corporation, and we would like to thank Lubna and Bala from Pelmorex for their input and support. The outline of the talk is as follows. We first go over the problem description, then we introduce the model that we use to do the analysis, then we present the main results and also discuss future research. Let's start with the problem description. In the paper, we consider bidding strategies for online ad auctions. So let's first discuss what an online ad auction or an online ad market is. So we're considering an online ad market that has three main players: the end users that access sites or a mobile app, an ad exchange, and bidders. A transaction in an online ad market starts when an end user accesses a site or a mobile app that has an ad spot where an ad can be displayed. When an end user does that, it triggers a notification to the ad exchange that such an ad spot became available. The ad exchange then forwards this information to the bidders in the form of a bid request. So a bid request notifies the bidder that an ad spot became available and also provides information about the ad spot. For example, demographic information about the end user, such as gender, age, and also the location. The bidders can then decide whether they want to bid for this ad spot or not. If they decide to bid, they have to specify the bid value with which they want to bid, and also the ad that if they win, that should be displayed at the ad spot. The ad exchange then collects all these bid replies and uses a second price auction to determine the winner of the auction. So the winner is the bidder who indicated the highest bid value, and the winner pays the second highest bid value in order to obtain the ad spot. The ad of the winner is then forwarded to the end user and displayed on the site or on the mobile app. So that's an online ad market. What we're going to focus on in this ad market is the decision process of the bidders for ad spots. So one question is, who are these bidders? And there could be different scenarios. So in one scenario, the bidders could be advertisers. So these could be companies that have an ad campaign and want to display their ad spots. Another scenario, and that's the scenario we're going to focus on, is rather than doing the bidding on their own, the advertisers actually hire a broker to do the bidding on their behalf. And in an online ad market, brokers are called demand-side platforms or DSPs. So here we're going to focus on the situation where a DSP bids on behalf of the advertisers for ad spots. In particular, we look at the situation of one DSP that represents one or several ad campaigns, and how the DSP optimally bids for ad spots for these campaigns or for these advertisers. So what we focus on is on demand-side platforms, DSPs, and we assume that we are given one DSP that represents several advertisers that have several ad campaigns. Each ad campaign is characterized by the following properties. So the first property is a targeting criteria. So which demographic should be targeted with this ad? So this could be information such as gender, age, and location. The second property is the duration of the ad. From when to when should this ad campaign run? And the third property is the number of impressions that should be obtained for this ad campaign. So an ad campaign could be of an advertiser, could be that advertiser said, I have an ad. I would like to display this ad to end users from the age 30 to 40, male or female, that are located, for example, in Toronto, Canada. And this campaign should run for 1 month, let's say in the month of August, and I want to obtain during this 1 month 100,000 impressions. What is an impression? So an impression is the number of times this ad is being displayed to an end user. Okay, or the number of times that the DSP successfully bidded and won the auction for an ad spot for this campaign. So what we want to focus on is how the DSP makes these decisions, these bidding decisions on behalf of the advertisers. So the decision process of the DSP is as follows. The DSP receives bid requests from the ad exchange. For each bid request, the DSP then has to decide whether this request matches the targeting criteria of one or more of the campaigns that it's representing. If that's the case, then the DSP has to decide for which campaign to use the bid request and also how much to bid for this request. Something to keep in mind here is that this bidding is done in real time. And so the decisions of a DSP whether to bid or not and how much to bid needs to be done in typically less than 100 milliseconds. Also, property is that the DSP receives a large volumes of bid requests from the ad exchange. That could be thousands of bid requests per second. So the algorithm or the bidding algorithm has to run very fast, very efficiently, and has to be able to make these decisions very, very quickly. And the focus of this paper is how to make the decision, and in particular, how to make these decisions optimally. What do we mean with that? So first, we have to decide define what's the objective function of the DSP. So here we consider the situation where the interaction between the DSP and the advertiser is governed by a contract. So for each ad campaign, the DSP has a contract with the advertiser. And the contract specifies a fixed amount of money or a fixed payment that the DSP receives from the advertiser to run the ad campaign. In return, what the DSP does, it acquires on behalf of the advertiser the required number of impressions that meet the targeting criteria. In this setting, the revenue of the advertiser is the fixed payment minus the bid cost, basically the cost that the DSP has to pay in order to get the required number of impressions. And the goal of in order to maximize the revenue, the goal of the DSP is then to minimize its bid cost or to get the required number of impressions at the lowest possible cost. And the focus of the paper is how to do that, how to get the required number of impressions at the lowest possible cost. So let's review the decision process of the DSP. So the DSP receives bid requests from the ad exchange. For each bid request, the DSP has to decide, should I bid for it? If I bid, which campaign do I assign the bid request to, and how much do I bid? And the goal of the DSP is to get, for its ad campaigns, to get the required number of impressions at the lowest possible cost. To analyze this problem, we use the following model. We consider a case where the DSP is required for each ad campaign to uniformly spread out the total number of impressions over the duration of the ad campaign, and needs to obtain an equal number of impressions during a number of pre-specified smaller time intervals, such as, for example, a day. In addition, we allow the DSP to break the time intervals over which a required number of impressions needs to be obtained into smaller so-called decision periods. The length of a decision period could be relatively long, such as an hour, or shorter, such as a few minutes. The goal is then to characterize how the DSP decides on the bid request allocations and the bid values for a given decision period. We model this problem as an optimization problem as follows. For a given decision period, let script N be the set of ad campaigns that the DSP represents. And for each ad campaign I, let capital I of I be the total number of impressions that the campaign is required to obtain in the decision period. In addition, we group the targeting criteria of the ad campaigns into a set script T of NR disjoint targeting groups. For each campaign I, let then script A of I be the targeting groups that match the targeting criteria of the ad campaign I. Similarly, for each targeting group J, let script BJ be the set of ad campaigns whose targeting criteria matches the targeting group J. Finally, we associate with each targeting group J a supply curve dj of B that characterizes the number of impressions the DSP obtains during a given decision period as a function of the bid value B. More precisely, if during the decision period the DSP bids with a fixed bid value B for all bid requests that match the targeting group J, then djB is the total number of impressions that the DSP obtains from the targeting group J over the decision periods. Here are two examples of such supply curves. These supply curves have been obtained from real-life data. On the x-axis, we have the bid value B, and on the y-axis, we have the number of impressions that are obtained by the DSP if the DSP bids with a fixed bid value B on all bid requests that match the targeting group J. Note that the supply curves are not continuous, nor are they convex. As a result, the assumption on the supply curves that we make for our analysis is that each supply curve is given by a non-decreasing right continuous function. Using these definitions, the optimization problem of the DSP is given as follows. For each targeting group J, the DSP has to decide on the fraction gamma ij of bid requests that are allocated to campaign I, as well as the bid value bij that campaign I uses to bid on requests of targeting group J. For a given decision period, the goal of the DSP is then to obtain the required number of impressions for each campaign I at the lowest possible cost. Here is the corresponding optimization problem. In this optimization problem, the objective function captures the total bid cost that the DSP has to pay under the assumption that the ad exchange uses a second price auction. The first inequality captures the constraint that the number of impressions obtained for each campaign needs to meet the required number of impressions, capital AI. The second inequality states that the total fraction of bid requests that are allocated for targeting group J cannot exceed 1. The last two constraints state that the bid values and the allocations cannot be negative. As the supply curves can be discontinuous functions and/or non-convex functions, the above optimization problem is not a convex optimization problem, and as a result, we cannot use standard techniques from convex optimization theory to compute an optimal bidding strategy. In the paper, we obtain the following results. We first derive structural properties of an optimal bidding strategy. In particular, we show that an optimal bidding strategy decomposes the problem into disjoint components, where each component consists of a set of campaigns and targeting groups. And the optimal bidding strategy can then be computed for each component individually. Using this result, we then derive an algorithm to compute the solution to the optimization problem that we saw earlier. We refer to this solution as a pure bidding strategy, as it uses for each campaign I a single bid value B star ij that the campaign I uses to bid for impressions of targeting group J. For the case where the supply curves are given by continuous functions, we show that this pure bidding strategy is in fact an optimal bidding strategy. For the case where the supply curves are discontinuous, we provide a lower bound on the cost of any mixed or randomized bidding strategy, where campaigns randomize the bid value with which they bid on bid requests for a given targeting group. Furthermore, we show that this lower bound is tight, and we do that by deriving a mixed bidding strategy that either achieves or can get arbitrarily close to the lower bound. Finally, we derive a bound on how much worse the pure bidding strategy performs compared with the lower bound on any mixed strategy. An important intuition obtained by the analysis in the paper is that computing the optimal decomposition of the problem into disjunct components is the key step to identifying an optimal bidding strategy. Once we have this optimal decomposition, computing the optimal bid allocations and bid values is actually not that difficult. Another important intuition of the paper is that for the case where the supply curves are given by discontinuous functions, for this case we have that pure bidding strategies might not be optimal. However, in this case, it's sufficient to consider mixed bidding strategies that use at most 2 bid values for each targeting group. The problem of deriving optimal bidding strategies for a DSP has been considered in the literature for the cases where the DSP represents a single campaign, or the DSP represents many campaigns where each campaign has an identical targeting criteria, or for the case where the DSP represents many campaigns that might have different but non-overlapping targeting criteria. To the best of our knowledge, the formal analysis of the general case where a DSP represents many campaigns with overlapping targeting criteria, which is the case that we consider in the paper, has not been considered in the literature and has been an open problem. Let's briefly discuss a possible direction for future research. Let's briefly discuss the direction for future research. In the paper, we considered a case where a single DSP represents several ad campaigns. Interesting future research is to consider the situation where several DSPs compete with each other and characterize the resulting market dynamics and market structure.